Now let's take a deeper look at the sliding window algorithm. Looking at a simple variation where the window is of a fixed size. Suppose we're given an array and we want to return true if there are two elements within a window of size k that are equal. And within a window of size k basically means that the window can be at most of length k. And the two elements have to be different elements. So we can't just say that this window has two elements that are the same because they're not two different elements, because it's just the same position. They have to be in different positions. Now suppose our k is 2. What would the answer be for this example array, and how would we determine the answer? Well, the brute force would be to look at every window of size k. So this is one window. Are these two values the same? Nope. This is another window. Are these two values the same? Nope. This is another window. Are these two values the same? Nope. Only if our window could have been of size 3 instead of 2, because then we would be able to have considered this window, and we know while these are not the same and these are not the same, these two are the same. But we can only have windows of size 2, so this doesn't work. We try the next window. These two are again not the same, but finally when we get to the end, this is our last window, these two values are the same. So brute forcing this is not too difficult. It might not be clear with a window of size 2 exactly what we would do, because with a window of size 2, we can just take the two elements and just check if they are equal. But of a variable window length that's even bigger, suppose 3, how would we do this and this and this? Well, we would do something like this, where our left pointer would represent the beginning of our window, and our right pointer in this case should never be at the same position as our left pointer, because then in that case we might compare these two and say that we found equal values, but they're not two different values. And let's say in this example our window is of size 3, just to illustrate the entire algorithm. So in this case, our right pointer is always going to be initialized to left plus 1, because we know our window is of size 3, but here we're checking for duplicates. We're going to check, is this left value equal to any of these other values in this window? And to do that, we're going to have a right pointer. So here our right pointer is going to be at this position. We're going to check, are these two equal? Nope. And then we're going to increment our right pointer here. Are these two equal? Nope. Well, we've gotten to the end of our window, right? Our right pointer can't be over here, because if our right pointer was here, then our window is bigger than 3. So to do that, what we're going to do is shift our left pointer over here, and then this would be our new window. We're going to have right pointer here, and then we're going to have it here. And then we're going to set our right pointer over here. These two aren't equal. Increment the right pointer. These two are equal, so we can return true. So that's essentially what I'm doing here. We have nested for loops. The outer loop is going to run as many times as how many elements we have in the array, which let's say is n. The inner loop is going to run roughly k times, technically k minus 1, but we still say it's k just for simplicity. K is a variable. It could be anything. It's safe to say though that k is going to be less than or equal to n, because we can't have a window that's larger than the array itself. But that would mean our time complexity is going to be n times k. Now for small k values, for small windows, that's not too bad. But for large windows, it could be worse. And really quickly, if you're confused by this line over here, this can be a sort of common technique with sliding window problems. We know that for every value here, we want to check, is it equal to any other values that go in the same window, and do that for every single value. By the time we get here, we have our window ending at the perfect spot. Well, in this case, we would check, is 2 equal to 3? Nope. Is 2 equal to 3? Nope. And then we would want to still start our left pointer over here. Even though we don't have enough values to create a window of size k, it's okay if we have a window that's smaller than k. So this window is still valid even though it only has 2 elements. Then we would check, is this left value equal to the right value over here? Yes, it is, so we would return true. When I iterate my right pointer, starting at left plus 1, going up until the minimum of the length and the minimum of left plus k, I'm saying, in this case, the length would have us stop here, but left plus k would have us stop at one element after that. But we know we don't want to end up going out of bounds, so we take the minimum of this and this, which would have us stop over here. So then we won't go out of bounds. That's what I'm doing with this line of code. But of course, it's not as efficient as we can have it. And what we're trying to do here is detect duplicates within a window. Detecting duplicates is something that can be improved with hashing. So we're actually going to use a hash set to optimize this to give us an optimized sliding window solution. And we could optimize it like this using a hash set to check for duplicates. Instead of having to manually compare every single element in the array to every single other possible value that could be in the same window, we can keep a rolling hash set of our window. Meaning that if this is our window, and we're going to continue to assume that, let's say k equals 3, if this is our window, then all three of these values will be added to the hash set. And as we go to the next position, because we just have a single loop here, we're iterating through every single position. That's our right pointer. By the time our right pointer gets over here, our left pointer is still going to be at 0. So what are we going to do? Because we've gotten to a point now where our window, or at least the pointers representing our window, are greater than the k value. That's this line of code over here. So what we're going to do is take the left value and remove it from our window, from our hash set, and then take our left pointer and then increment it to be over here. And so then this is what our new window is going to be looking like. First though, before we add this to the hash set, we're going to check, does this value already exist in the hash set? And that is a constant time operation. Instead of having this value and comparing it to this and comparing it to this and doing that for every window with every single value, we can do this in constant time with a hash set operation. In this case, 2 already exists in the hash set, so we can return true. Now, if it didn't, we would simply add this to the hash set and then continue the algorithm. We would then, add this value, pop this guy, increment our left pointer to be over here, and then, this would be the new window, and we would keep going just like that. And we would even get to the small window cases where we have a window of size 2, we have a window of size 1 until we get to the end of the array. And if we never found a window that contained duplicates, we would end up returning false. This is the relatively simple sliding window case where we have a window of fixed size, but we know that's not always going to be the case. As we saw with Kadane's algorithm, the sliding window variation, our window could be of variable length, right? We showed a case where we had a window with 1, then 2, then 3, then 4, and then it skipped. We removed all these and then we had a window of 1 again. So that's what we're going to be focusing on next.